logs, we're talking about raising a number by the powers of 10. Okay? Which is why, if you look on your calculator, don't it have like log 10 on there, on your advanced calculators? Okay? So, that's what this is. So, specifically, the log number represents the number of tens that are multiplied to create the original number. So when we're talking about a logarithmic scale, that means you need more than one number. You know, we're going to need the original number to fix and the ending number, or the ending number. Okay. So when it comes to logs, it's really easy to do by power of the 10, because an example would be a log of 2. Basically, we're just counting numbers of zeros, right? Because 10 times 10 equals 100. That equals a log of 2. Okay. So we have a log of 4. That's going to be 10,000. Okay. Or 10 times 10 times 10 times 10, or 10 to the 4th power. I don't have it up there. All right. So easy way to remember this is to count the zeros, but this technique only works with powers of 10. All right. So.
Wait, I'm sorry. What was the definition to logarithm?
Oh, really? Oh, it's not on there? I don't write it. It's not. A quantity representing the power to which a fixed number must be raised to produce. It's on there. It's not. I get gone. I did make some adjustments over the weekend, but bang, get your picture if you need a picture right there, guys. A quantity representing the power to which a fixed number must be raised to produce a given number.
Okay.
Screw. Okay. And that's the definition out of the dictionary. Right? We'll get kind of more in the explanation in 1 second. Okay. So that's kind of confusing, guys. I was looking up YouTube videos all weekend to figure out, man, how can I show them a video that's going to explain what a logarithm is much simpler? Come to find out, all these videos are pretty complicated in how they're explaining what a logarithmic scale is. So I like the way the book explains it the best, as far as like everyday terminology, how we use it, because it was really based on the physics of sound in general. All right? So an everyday logarithmic scale that we know about, you know, even though we don't live in California, we don't deal with tectonic plates, would be the Richter scale, which measures the strength of earthquakes. All right? So when we remember, a logarithmic number is a comparison, meaning we need the initial and the ending. Okay? So we compare 2 earthquakes. I like the example the book gives you, one with the magnitude of 5 and the other the magnitude of 7. We clearly see the difference is 2 points. Just the difference between those two numbers is 2, correct? Mm-hmm. 7 minus 5 is 2, you know. So that's going to let us know, because each point indicates the strength that the earthquake increased tenfold. Remember, 10 times 10, that's how we get, 100, which is a log of 2, correct? Like I said, just count your zeros when you have a number that is divisible by 10, all right? So therefore, a 2-point difference indicates that a larger earthquake, the 7, rated at 7, is 100 times stronger than a smaller earthquake of 5. Okay? So we had, again, I was kind of explaining this the other day in class, and we have one earthquake that's 20 and one earthquake that's 14. That would be a log of what? A log of 6, right? A log of 6. Log of 6 equals 10 to the 6th power, correct? 10 to the 6th power, how much does that equal? How many? A million. The 6 zeros would equal a million, all right? So that's going to equal the 2, with just the difference between those two. That would be the log number.
But the 100, you got it off this? Where'd you get the 100?
We're not on decibels yet. We're not. They relate, but we're not on decibels yet. I got the 100 because we're doing it in factors of 10. 10 times 10, 10 times 10 times 10, are just powers of 10. Okay? Just like the book kind of gives you right there. So again, our first number was what? 20 and 14. That would be the difference between those numbers would be 6. That would be our log. A log would be a log of 6. That number in real time, as far as strength goes, would be 1 million. Just add 1 plus the 6 zeros, because whether it be 10 to the 6th power or 10 times, I'm sorry, this is kind of sloppy, times 10 times 10 times 10 times 10, that's all gonna equal 1,000,000. Boom, boom. Okay? Trying to make that simple, guys. However many zeros it is, that's how many you're gonna add behind the number 1. Okay? Or if you have your calculator, which we probably won't need it, I'm telling you guys the most easiest way to learn that, we just be to count your zeros. Okay? So if I give you a problem, it may be similar to what I'm asking. You know, I may give you 2 different numbers, and then you have to figure out the log, and then I may ask you what the log is. I may ask you, so if I give you the number of 10 million, and I may ask you what is the log of 10 million, you're going to say 10 to the 7th, right? Or I'm sorry, log of 7.
7.
Right? Take 7 zeros to make 10 million, correct?
10 million.
I just added 1 to this right here. Boom. So that would be a log of 7, right? So just count your zeros. That's the easiest way to explain it. The book explains it really well as far as that goes. Okay?
So is log always 10?
Yeah, log is always by power 10 because you're taking a really big number like 10 million and you're expressing it in an easier format by saying it is a log of 7. Meaning that from from our earthquake, say for instance 20 and 14 would be the log of 6. That's like saying that our earthquake that's at 20 rating is 1,000,000 times stronger than our log of, our earthquake rated at a 14 on the Richter scale. Even though hopefully it never gets that high because that may make the whole United States fall off or something like that. You know, I'm just using those numbers as examples. Okay. Golden? Golden retriever? Sweet. All right, guys. No questions on logs, right? Remember, I may ask you, what is the log? I may ask you, how many times stronger? Okay? All right. So, let's talk about decibels, guys. Decibels are a unit used to measure the intensity of sound or the power level of an electrical signal by comparing it with a given level on a logarithmic scale. Again, guys, decibels are underneath the umbrella of a logarithmic scale. Okay? Not the other way around. Okay? Again, the book states decibels are a unit used to measure the intensity of sound or the power level of an electrical signal by comparing it with the given level on a logarithmic scale. Right? And of course, the decibel is the unit we use to measure that. Okay? In ultrasound, it is important to quantify the strength of sound beams as they are created and propagate through the body. Okay? Also, electrical signal strength and brightness of images need to be quantified. The decibel is a common unit for measuring these signals. These are just some facts about logarithms. So if you in your book, highlight these. Okay? Decibel notation is logarithmic, as I stated earlier. It's based on a logarithmic, meaning that it's based on the power of 10. I'm going to explain why they come with that number 3 in a minute, okay? All right? So just like the paper I handed out to you guys right here, you can see that they still have decibels. The conversion table right here is still by powers of 10, right? Same difference, all right? So decibel notation doesn't measure absolute numbers, guys. It's a relative number because it's not exact, okay? Relative means it's not exact, okay? It just measures relative changes. You know, about, this earthquake that was 20 is about 1,000,000 times stronger than an earthquake that was 14. It's not exactly 1,000,000 times stronger than the earthquake that was 14, okay? Just relative changes, all right? Decibels require 2 intensities, the reference or the starting intensity and the actual level or the intensity where it ended up at, okay? Decibels are a ratio. The measured level is divided by the starting level. And that's how we just get our difference right there, right, guys? That's how we get our difference to figure out our log from earlier. All right? So, important things to know about decibels, guys, is, again, decibels are a relative measurement. Okay? It's not absolute. It's not absolute. Logarithmic numbers aren't not absolute. Okay? It's a comparison between actual and the starting point and the ending point. Okay? it is a ratio as well, because we need both of those numbers, okay? And it's logarithmic. Okay? Those are some facts you need to know about decimals and decimal notation. All right? This right here, guys, is just a scale of different, decibel intensities, or, So, again, you would think a decibel of 0 would mean that that's just complete silence, right? When we're measuring decibels, a decibel of 0 is just the absolute level threshold of human hearing, okay? That's not everybody's hearing, because all of our hearing is different, right? But it's about the average, about what the lowest intensity that a human can hear. Okay, so when we're talking about decibels, we're talking about actual human hearing, okay? Okay, decibels are also Bell's itself is also a unit by itself, right? Bell's created by Alexander Graham Bell, who invented the telephone, and deci in a bell equals a log of 1. Okay, we're going to fill this chart out in 1 second, okay? A bell equals a log of 1. What does deci mean, guys? Remember we talked about this. How much?
10.
10? A tenth. A tenth.
10.
Okay? So a decibel is 1/10 of a bell. Okay? So in that case, 1 bell equals 10 decibels. Correct? 1 bell equals 10 decibels. Okay? So just trying to go through our chart a little bit, guys. So we get a little better understanding. Okay. Right and ready, guys. I want you guys kind of help me fill it out as I go across it. Okay. So let's do this. All right, guys. So we have this is our log 10 scale right here. 10 to the first power equals what, guys? It's 10, right? So it's gonna be. I wouldn't get the worst pen up there. Worst marker. It's gonna be 10 is gonna be just a factor. That's the amount that it equals, right? Okay. Again, 10 is gonna a log of 1. Which is what this is, 10 to the first power, that's a log of 1, okay? That's going to equal 1 bell, okay? 1 bell, all right? So we know a decibel is a tenth of a bell, so we move that over from the base number, which is the bell, over to deci. We're only going to have to move it one time to get to the decimal, because it equals 1/10, right? So that's going to equal 10 decibels. 10 decibels right there. Okay? And you can see on your chart right here, which is also logarithmic. All right. Again, I'm going to explain where the 3 comes in later. All right. But this, in the meantime, let's do this right here. All right. So 10 to the second power of log of 2 is going to equal 100, right? So if we see that number 100, we know that the difference between those two intensities is going to be increased by 100 times stronger, correct? We have a log of 2, that means it's 100 times stronger, all right? So that's going to equal what? 2 bells, right? Whatever the exponent is, that's going to equal the number of bells, okay? Our decibels also going to equal, it's going to be what? 20 now, right?
Yep.
20 decibels, okay? And so you're just basically going to...
1 divided by 2. 1 divided by 2.
Say that again.
I'm sorry?
How did you get the 20?
20, that's how, because we're just moving from, the bell is the base unit. I'm just adding the bell.
So it's not
So you,
100?
No, no. It's
No.
just 1 divided
the
by 2.
100 is the factor.
Oh,
Is the factor that it increased by. Remember, 20 decibels equals an increase of 100 times. So again, when we're talking about decibels, you can just look at the first number, and that's how many zeros you're going to add to that to figure out the quantity or the factor. So same thing right here, 10 to the third. That's going to be
1,000.
1,000. That's 3 bells.
30.
Decibels is going to be
30.
30 decibels. Okay. So when you're talking about on our on our decibel scale on this left side right here, you see how I just increased. We're just, however many decibels, if it's 40 decibels, we're just gonna add four zeros to the power of 10. All right, so right here we got 10 to the 6. That's gonna be, we already did this one already.
Million.
It's gonna be 1,000,000, right? Right there. That's gonna equal 6 bales. Again, I included the bales so you know whatever the
60.
log is. That's also gonna be what the base or the bale is gonna be as well. Okay? Which is also gonna equal 60 decibels. Correct? So we have 60 decibels. That's gonna be equal to 10 to the 6 as far as our log scale. It's also gonna mean that between those, the relative change between those numbers are gonna be 1,000,000 times. The larger number is gonna be 1,000,000 times stronger than a smaller number. Remember, it's relative, so it's about 1,000,000 times stronger. Okay? So I'm gonna come back and explain